Yes, indeed. Thank you to everybody who came here on this morning to honor Andrei's memory and his mathematics and celebrate his life in the best way possible. I'm not going to talk much about Andrei, specifically at the beginning of my talk. This is not a funeral. We are here to discuss mathematics. I'll just say that he was a wonderful mathematician, a dear friend, and I will want to call him, forgetting that he is not among us anymore, many times, I'm sure, over the coming years, and then realize that he is no longer with us. Andrei's mathematics had very distinctive flavor, both in style and substance. I think he was very consistent throughout his mathematical life. I think that he, in his heart, he was a representation theorist, I would say, owing to his beginnings with Joseph Bernstein, who is here, who was really his de facto advisor, I would say. But also his the kind of representation theory and algebra that he did for most of his life had always had a distinct combinatorial, concrete flavor. He was not into general nonsense and abstraction. He was always into specific examples and constructions, and trying to understand things at a very, in a very direct and combinatorial way. This is how I understood it. This is what made it easy for me to collaborate with him. I think that in all of his mathematical pursuits, Andrei always strove for clarity. I think this was his main goal in doing mathematics. He wanted things to be crystal clear, and clear doesn't mean simple. It's as well, I guess. He's another advisor and mentor, Israel Gelfand, used to say, I don't understand complicated mathematics, so make it simple so that I could understand. But as Einstein said, make everything as simple as possible, but not simpler. And that's what Andrei did. So he just wanted to clarify the essence of each important mathematical issue, the issue that he felt was important for him to resolve. And if the answer is complicated, then that's life. He just what we shared. We had very different persons, but what we clearly shared, I think, is the Platonistic view towards mathematics. Mathematics is to be discovered, not invented. And so it's not up to you to decide whether the answer is simple or not. What's up to you is to clarify the essence and also strive for clarity in form, not just in substance. Find a clear way to present it, find the right notation, right terminology. He worked relentlessly at perfecting his exposition, and he was a wonderful teacher as well. He spent several years teaching without any kind of pay, and in fact enduring great dangers at an underground outfit in Moscow, where Jewish students not admitted to Moscow State University were taught. Some actually, there is at least one, at least two students from that time here in this room. 3, okay. And he also taught in math circles for high school and junior high school children. I think partly the kind of mathematics he was interested in was well suited for this type of these types of pursuits, but also one has to have a desire and willingness to donate one's time and effort to these types of activities. So in this talk I will, well, it's impossible to emulate. I won't try to do it the way Andrei would do, but I would try to cover several of his theorems that he proved, and choosing the ones which are easiest to formulate, easiest to understand. So these are not going to be his most important achievements by any measure. These are just some morsels, some examples of beautiful mathematics that he created or participated in creating with his collaborators. The choices obviously will reflect my personal tastes, so they will be more combinatorial, which is also, I guess, makes it easier to explain. And I will discuss them in roughly chronological order. There will be many, many things that I will not talk about that Andrei did. And I am going to very quickly mention some of them, just so that you can recall or at least appreciate the great variety of mathematical subjects that he worked on. And if I don't mention particular work, maybe joint with you or something, it doesn't mean that I am going to cover it in my talk. So this is a subset of what will not be covered. I won't talk about his very early foundational work on p-adic representation theory with Joseph and single-authored. I won't talk about his work on small resolutions of singularities of Schubert varieties and Grassmannians, a very influential piece. I won't talk about hypergeometric functions, GKZ theory with Guilfand and Kapranov. Nor will I talk about multidimensional determinants, which you so wonderfully discuss in your book. In fact, maybe I should mention that some of you might be under a false impression that I was his main collaborator, but actually he wrote more papers with Misha and Israel Moiseyevich than he did with me. So certainly they were his main collaborators numerically, at least, but also maybe substantively. I won't talk about his work on string and canonical basis with Retach and Berenstein. Yeah, we haven't started mathematics yet, so just which in many ways presaged the introduction of canonical basis by Lustig and Kashiwara. I won't talk about his work with Madyar and Weyman on classification of generalized flag spaces with finitely many orbits. Nor will I talk about our joint work on total positivity in Lie groups, which was inspired by Lustig's work, but was made much more concrete and combinatorial by us. I won't discuss his work with brothers Shapira and Weinstein, where they solved in full generality Arnold's problem of counting connected components in double real Brouillard cells in Lie groups. And I won't talk about cluster algebras at all. So, including various applications of them. So, what is there? What is left? There's still a lot. So let me start. So my first topic will be what Andrei called PSH algebras, which stands for positive self-dual Hopf algebras. So this project grows out of. So this was published in his book, in his Springer lecture notes volume in 1981. I remember at the time seeing that volume and thinking, how can one living in the Soviet Union publish a book in Springer Verlag? This was inconceivable because of the lack of communication. I don't know, maybe Joseph remembers how this was arranged, but I would, at the time, to me, this seemed like impossible to do. Yeah. Uh-huh. Mm-hmm. So he didn't really pay much attention to what was expected of him as a Soviet citizen. That's right. Right. Oh, I see. Okay. Well, so what's the question that this construction is trying to answer? As many of you know, the ring of symmetric functions is a fundamental object. Yeah. Oh, you can sit here. Yeah. The ring of symmetric functions is a fundamental object in algebra and many parts of mathematics. And for example, there are like the three instances, three contexts which immediately come to mind is representation theory of general linear groups, representation theory of symmetric groups, and Schubert calculus on Grassmannians. And then there are some other contexts. So people like myself wondered, why is it so? Is there some functorial way to relate these contexts? Is there, is this all just, as Giancarlo Roda would say, cryptomorphic to each other? So just we are using different languages, but really talking about the same thing. And the answer is, as I see it, the answer is no, it's not all cryptomorphic. These are distinct contexts. But there is an underlying reason why this object comes up here and there and there, and it's because it can be defined axiomatically by a very natural set of conditions. And those conditions are satisfied in various contexts, and that's why you get the same answer. That's the point of view. Okay, so let's assume that A is a graded connected. Connected just means that in degree 0, it's one dimension, just the field, the ground field. or Z. Actually, we're going to work over Z. Hopf algebra over Z. So this just means, in case you forgot, that you have a product and a coproduct, and then the antipode is unique. So you have multiplication and co-multiplication, and one is, one gives you a homomorphism with respect to the other. Okay, and so let's suppose that you have a basis. Okay, so the secret thinking behind this is that A is actually like ring of symmetric functions. Okay, and in the ring of symmetric function, you have the symmetric function just means polynomials or formal power series and infinitely many variables which are symmetric in those variables. And you of course can multiply them, but you can also co-multiply, which means you split the set of variables into two subsets, and then you get canonically an element of the tensor product of your algebra with itself. So that's a coproduct. Okay, so that's what A is supposed to be. Sigma is like Schur functions. Okay, but we're not allowed to say that. So sigma is a Z basis of homogeneous elements such that, and then the conditions are, first condition is that A is self-dual with respect to this basis. Self-dual simply means that product and coproduct are basically the same when you dualize. So in other words, the structure constants are the same. When you multiply two elements of your basis and expand in terms of the basis, you get some coefficients, structure constants. And when you split an element of the basis and write it in terms of tensor products of elements of the basis, you also get structure constants, and they are the same. But more importantly, perhaps, those structure constants are non-negative. So, for example, in representation theoretic context, these are multiplicities of irreducibles and some products of representations. In Schubert calculus, these are intersection numbers, which are non-negative because everything is oriented. So, anyhow, you have something like this, and then basically, morally speaking, there is nothing but the ring of symmetric functions, but you can't quite say that because you can tensor multiply those rings, right, and tweak the grading, like multiply the degree of each element by, 7, right? Okay, so we have to, just because we want to be clear, we want to say it more precisely. So if sigma contains only one primitive element, I'm not going to explain what that means, say of degree 1, or else rescale the grading. So, which means, in fact, if it's not of degree 1, then everything is in degrees which are multiples of that, and you can just change the grading, and it will be like this. Then A is canonically isomorphic to lambda. Lambda is everybody's. You cannot see this, right? So I should move probably. Oh, okay. Well, I want to finish this line and then I'll. Okay. It's not required. Yeah, which is kind of surprising. Yeah, it's automatic. Whether we know that this is commutative or co-commutative. Yeah, and I think it's not required. But not just so lambda is the ring of symmetric functions, but not just abstractly, but canonically via. Okay, so let's say sigma consists of elements which we denote sigma lambda, where lambda a priori we don't know that this runs over partitions, but if this happens, then it will, and the mapping is just what you think. It's we just identify sigma lambda with the Schur function S lambda. Okay. In fact, there are only two such isomorphisms. You can also twist by the involution omega. Those of you who know standard theory of symmetric functions, the involution that transposes the shapes. So there are two. So it's not canonical. It's like canonical up to that twist. But anyhow, the point is that it exists. That there exists such an identification, and of course, then of course, this implies, that of course structure constants are the Littwood-Richardson coefficients, because that's what structure constants in the ring of symmetric functions are. Okay, so but more generally, when you don't have this condition of having only one primitive element, then you just need to take tensor product. Any A like that is canonically isomorphic to a tensor product of algebras as in star, where this is star. Okay, so essentially, take several copies. In each copy, choose rescaling of grading any way you please. Then take a tensor product. So, or in pedestrian terms, take symmetric functions in several sets of variables, each of which is weighted, by some positive number. That's really what tensor products are. Okay, so you might think this answer is not, elegant, or maybe it could be simpler, but like I said, it is what it is, and you cannot make it simpler, and it clarifies what's going on really. So each time you see something with these properties, then it can't be anything else. So that sort of explains why symmetric functions and Littwood-Richardson numbers are so ubiquitous in mathematics. At some level. I mean, it doesn't explain everything, but yeah. Questions? Because I'm moving to the next topic. Okay, so the next topic, number 2, is associahedron as a secondary polytope. This is joint work with Kapranov and Guilfand. From 1990, and I guess the book was published in 1994. Okay, so what's an associahedron? Associahedron is a cell complex that was defined by Stashev in the 50s, I think. And basically, what you do is you take a convex polygon, you triangulate it by diagonals. These triangulations, there are a Catalan number of them, are related to each other by flips. So you fix all diagonals except one. You remove that one diagonal. That's what I just did. And then, well, there is one quadrilateral region, and you stick in a diagonal in a different way from the one that you had before, so it has to be this one. Okay, so these are edges of your graph. So the vertices are triangulations, the edges are flips. Okay, and then you can define higher dimensional faces by looking at syzygies, by looking at relations among flips, cycles, and filling that in by two-dimensional faces and so forth. So the name associahedron comes from the fact that when you just write the associativity axiom, the flips will correspond to local changes in bracketings, and so these cycles that I just mentioned, they correspond to the syzygies of the associativity rule, and then higher homological objects, as you syzygies among syzygies and so forth. Okay, so you define this complex. What's amazing is that this turns out to be a polytope. So this is not just a graph, but it's a skeleton. Let's just talk about the one-dimensional portion, right? 0 in one dimension. So we just have these triangulations and flips, and it's not just a graph, but it's a skeleton of a convex polytope. Okay, and the story of proving this is kind of complicated. So there is a belief that Milner already knew this in the 60s, but there is no surviving record. Mark Heyman proved it in 1984, and there is a surviving handwritten manuscript which wasn't published. Maybe he thought it wasn't worth it. And then finally, Carl Lee had the first published proof in 1989. So this is polyhedrality. I don't know if this is a dictionary word. So what they did was they used a technique called shaving, which is something like this: that if you have if you have a polytope, you understand it on a combinatorial level, then you can take let's say an edge or some other face of it, and take a knife and just cut it along that edge, right? That changes the combinatorics in a controlled way. You can exactly describe what happens, right? And then you can shave, along a two-dimensional face, and then again one-dimensional, whatever you want, right? And you can control what's happening. Of course, there will be a hierarchy of epsilons, because each time, you will have to be more and more delicate with your shaving. But that's how you shave, right? It's just anyway, I just thought about it. Maybe it's not appropriate. So it doesn't really explain anything, right? It explains, it proves that it's a polyhedron, but clearly there should be a better reason for it being polyhedral, and that reason was provided by the theory of secondary polytopes that was developed by these folks, and then, of course, then extended by Belair and Sturmfels. So anyhow, this is a classical by now subject. So I will just explain in pedestrian terms what it means for this example. Okay, so what it means is the following. Okay, so secondary polytope construction. So this was GKZ. And by the way, later it turned out that this is not the only explanation. So this is so there are other natural constructions of other natural realizations of the issosahedron, which are not a fine equivalent to this one, as established recently by Ceballos and Ziegler. So there is in particular the issosahedron arises naturally in cluster theory, which I'm not supposed to talk about. So Chapaton and us, we proved that, and we constructed a realization which is different from the one that I'll be talking about now. Children? And also, there is another realization of an issosahedron as a Minkowski sum of simplices, which was in this form suggested by Sasha Postnikov, but earlier in a different language by Lode, and then later rediscovered by various other people, Schneider-Sternberg, Rothe, Santos Streinu, and Buchstaber. But anyway, this is not what I'm going to present here. So what's the secondary polytope construction? That was historically the first natural polyhedral realization of the issosahedron. So you start with, what you do is you actually realize your convex polygon metrically. So you let's say this is not, you choose some coordinates, Euclidean structure, whatever, on the plane. So you choose a particular realization of the polygon, right? The combinatorics doesn't depend on which polygon you take, but I want you to fix it. Then you, for each triangulation, okay, maybe I should parallel what's drawn here. Let's say this is what I chose, okay? And maybe behind the blackboard there is this. I don't know. This is the grid, into units, squares, right? Okay. And then you take your favorite triangulation, like this one. Okay. And then for each vertex, you sum the areas of the triangles adjacent to that vertex. Okay, so for example, for this vertex, you have this triangle whose area is 2. Okay, sorry, it's 1 really, but rescaled area is 2. Okay, so let's multiply. Let's make it so that the smallest area of a lattice triangle is 1. Okay, so multiply all areas by 2. So then the area of this triangle is 2. The area of this triangle is, what is it? Oh, this is not a lattice triangle. Okay. Huh? I need to change the lattice. So maybe I need to, let's just make it like this, which doesn't look, okay. Now this is 2 also. This is 1. And this is probably 3, right? Am I right? David? Okay, let's assume I'm right. Yeah, because it triangulates into this one, and that one. Okay. And then what you do is you add up, at each vertex you add up the areas of the adjacent guys. 2, 4, 5, 4, 1, and 8. Okay? So these pink numbers make up a vector. And there is a vector like this for any triangulation. So these are points in the 6-dimensional Euclidean space. You just take those points, you take their convex hull, that's it. So the edges of that convex hull will exactly be the flips. And it will be the same combinatorics regardless of which convex polygon you started with. I find this amazing. I mean, maybe by now, Misha, you don't find this amazing anymore. You're not, because this was superseded many, many times and developed and so forth. But I think if we return back to the times when this was not invented but discovered, then yeah, we should be in awe of the beauty of this construction. Okay, my third topic is going to be BZ triangles. This is with Berenstein. From 1992. I think Arkady was the first student that Andrei had, probably. Depending on the definition. Anyway, the first one that I know about. And this is, of course, this is a rule. This is a polyhedral rule for Littwood-Richardson numbers. So the Littwood-Richardson numbers I already discussed earlier. They are these structure constants for the multiplication of Schur functions. Obviously, I didn't define what Schur functions are and so forth, but I assume that many of you know it. Huh? That's right. Yeah, that's right. This is a rule that describes these numbers as number of integer of lattice points in certain polyhedra or polytopes. And this was put to great use. This was the foundation for subsequent work by Alan, who is here, and Terry, and which also was based on earlier work of Klitschko in their proof of the Horn conjecture. So, but from a combinatorial standpoint, the problem that this construction solved was to give a rule that manifestly exhibits the order 3 symmetry of these numbers. So exhibiting the order 3 symmetry. So when you there is a way of thinking about triples of shapes, which is symmetric in the 3 shapes. Okay, so you take one of the shapes and let's say take a complement of it inside some ambient rectangle. Then these numbers are just intersection numbers for triples of Schubert varieties, and so there is a symmetric group S3 acting on that. So it should be, or representation theoretically, these are dimensions of SLK. Spaces of SLK invariants into tensor product of 3 reducible reps. So it's there is a basic order 3 symmetry. Unfortunately, this rule doesn't exhibit full S3 symmetry; it just exhibits cyclic symmetry of order 3. But I believe that before this work, there was no rule known that would show this order 3 symmetry at all in any form or shape. In fact, the full group of symmetries is S3 cross S2, and I believe the problem of finding a combinatorial rule which is manifestly symmetric with respect to this full group of symmetries is still open. They do some of it, yeah, but yeah, I'm not quite happy with that, but maybe. Yeah, that's my problem. I don't know. Yeah, I know about that work. Yeah. By the way, in an earlier work done in early 80s, Andrei introduced a rule which he called pictures. These combinatorial rule for computing intertwining numbers for pairs of skew Specht modules. So basically, you take two skew Schur functions and you want to compute their inner product, right? So if one of them is a straight shape, then this inner product is exactly the Littwood-Richardson number, a general Littwood-Richardson number. But when you state it this way, it's a more general concept. And of course, it should be symmetric in the two skew shapes involved. So there is a beautiful rule which I reproduce in a slightly different form in the appendix that I wrote for Richard Stanley's enumerative combinatorics, which is also where this example that I'm going to present to you is taken from. So, yeah, maybe I should give some more readable references for this. So, for the previous topic, well, of course, here nothing is more readable than the book. So I think I already did that. The PSH result is discussed in a very nice way in the book by Schneider and Sternberg, and also very recently in beautiful notes written by Victor Reiner. So called something like Hopf algebras and combinatorics. So you can Google it. Okay, so back to BZ triangles. Suppose we have. By the way, this work was later extended to other types, but I'm not going to talk about this. Okay, so suppose we have three shapes, lambda, mu, nu. By a shape, I mean Young tableau like this. Young diagram, sorry. And of course, we want lambda to be of the size equal to the sum of the size of mu and nu. So total number of boxes in lambda is the sum. Okay, now lambda, let's say, is lambda 1 greater than or equal lambda r, and then mu similarly, and then nu similarly. So now we introduce a slightly different notation to make this thing symmetric in particular. So I'm defining mi to be mu I minus mu I plus 1. So I just take these differences, which are, of course, non-negative by virtue of this condition. Here I runs from 1 to r minus 1. And similarly for n, with respect to nu, so I'm switching from the Greek alphabet to the Roman one, as Romans did. And for lambda, I am doing the same, but I want to reverse the order, flip the order to make this thing symmetric in the three partitions. Okay, so Li is going to be also L sub something minus, lambda sub something. And that something is going to be r minus I here and r minus I plus 1. Sorry, r minus I plus 1 here. Okay? So now I have three vectors, L, M, and N. These are r minus 1 dimensional. Okay? And so the theorem, due to Bernstein and Zelevinsky, asserts that this number, the Littwood-Richardson number, C lambda mu nu, is equal to the number of certain BZ triangles. Different people use different. There are different versions of this result. I'm just presenting one of them. With parameters L, M, N. And I guess R is also a parameter, but yeah, built in. So let me just show you an example. Let's say R equals 4. So I didn't define what BZ triangles are, so I'm going to define it now. You wouldn't listen to me if I didn't tell you why I need to do this. So, okay, so lambda is 4, 4, 2, 1. Mu is 2, 1, 0, 0. Nu is 4, 3, 1, 0. Then n, the differences are 1, 2, 1, right? 1, 2, 1. Then m is 1, 1, 0. And L, now we're writing it backwards. 2 minus 1 is 1. 4 minus 2 is 2. 4 minus 4 is 0. So it's 1, 2, 0. Okay? And now what I want is I want to fill out a triangle with numbers, except for the corners. Okay, so here is one filling that satisfies the conditions. I'm not telling you what the conditions are, but you will see it in a moment. Okay, so just any integers, not necessarily positive, satisfying these conditions. So what are the conditions? The conditions are that when you add the numbers along the columns like this, okay, add all the numbers, you get 1, 2, 1. Okay, you get n. Now rotate 180 degrees. You add numbers like this, like this, like this. You get 1, 1, 0. That's m. And finally, you read by rows. The sum is 0, 2, 1. But, of course, we read it. Okay, we read everything in the counterclockwise direction, right? This is reading direction. Okay, 1, 1, 0, 1, 2, 1, and 1, 2, 0. That's L. Okay, that's not enough, of course. This would just be a fine subspace. But the condition then is that not only is each of these sums what the doctor ordered, but every partial sum, as you compute it in the direction shown, must be non-negative. Okay? All partial sums are non-negative. So that's the polyhedral condition. Okay, so like 2 is non-negative. 2 and minus 1 is non-negative. And then you add 1, it's still non-negative. Okay? So the number of ways to fill a triangle satisfying these equations that I started by and these inequalities is exactly, that's the theorem, is the Littwood-Richardson number, and obviously this has this symmetry of order 3, manifestly. Okay. Once you have one polytope, then you can massage it in different ways and get some other polytopes out of it. So there are other versions. Okay. Questions about this? Well, as Bill Fulton taught me the main goal of a math talk should be to inspire listeners to go home and read the papers. So, in this case, yeah. Anyway, that's. I think it would be great if I achieved that. If more people would read Andrei's papers as a result of this. Example number 4. That's probably all that I will have time for today. Is our work with Andrei and Berenstein on matrix factorizations. This is with Arkady and myself in 1996, and was extended later to other Lie groups and more general settings of double Brouillard cells in our subsequent JAMS paper in 1999. Okay, so this is the only example where I also collaborated with Andrei. Okay, so what's the problem here? We want to understand the multiplicative structure of matrices. I mean, like how matrices multiply. Okay, yeah, I know it's impossible. It's like the meaning of life. But so, and here is a naive question. You know, when you want to understand how positive integers multiply, right? You first identify the simplest factors that there can be. These are prime numbers, and then you try to factor other integers into those factors, which is a difficult problem, as we know, right? So what would be the analog of this question in GLN, in the general linear group, in the world of matrices? Well, you want to understand what are the simplest possible factors for matrices, and then factor into those factors. Okay? And well, the simplest, of course, then again, it's subject to debate, but one way to answer this question is that you want to factor a matrix into elementary factors. Let's say this is not a term that we use, but which are as close to the identity matrix as possible. Okay, obviously you cannot factor into identity matrices. This would be marvelous. But the next best thing is an identity matrix with a little speck. No, that's not a good word. With a little, a perturbation. Okay. So what would be such a perturbation? Well, you just put one non-zero entry off the diagonal, and of course you want that entry immediately next to the diagonal, because otherwise you can factor. So so you want to minimize sort of the supply of the factors, and so it's a natural thing to do to put some number t, let's say, above the diagonal, and zeros everywhere else. Okay? So something like this. This would be E2 of t. 2 pinpoints the location where you put the t. Okay, so there are 1, 2, 3, 4 possible locations. But then, of course, if you just have factors like this, then you can only generate upper triangular matrices. So you want something below. Let's say here. I'm not going to write the zeros anymore. So this would be F2 of t. And then you might also want to take, perhaps, put something on the diagonal. if you want. Well, there could be different conventions. If you want to do it in SL5 in this case, then you want to put T and T inverse here. Anyway, maybe that's what I should do if we want to factor matrices of determinant 1. Okay. Anyhow, so these are like the simplest matrices multiplicatively there are. And then you ask, how to factor a given matrix into such factors. Well, there are two stages to this process. First, you need to decide on the combinatorics of your factorization, where these things will be placed, right? And then you need to determine the parameters of the factorization. Okay? Of course, you can only hope to do this when you have as many equations as you have unknowns. So you want, if your matrix is an n by n matrix, then you want n square factors, or maybe if it's an SLN, then n square minus 1. Okay? So how do we do this? Well, the first step is kind of clear. We just split the matrix, do the Gaussian decomposition. You split your matrix into lower triangular, unipotent, diagonal, and upper triangular, unipotent. Of course, there are issues. It may not split like that, but let's say we're interested in doing this birationally. So we're dealing with generic matrices. So your matrix doesn't satisfy any equation that on a finite list that some malicious fellow wrote in advance. Okay, so you take your matrix and you factor it first into lower triangular, unipotent with ones in the diagonal, then diagonal, then upper triangular, unipotent. Okay, there are formulas for doing this in terms of some minors of your matrix, so this is easy. This is just basically Gaussian elimination. So, Kramer's rule and that sort of thing. Okay, so you can do this. Now the problem is splits into 3 problems. Of course, the diagonal case, this side is easy. And the upper triangular and lower triangular are essentially the same. Just transpose your head and read the proof for the other case. Okay. So let's say we are dealing with upper triangular matrices. So you take an upper triangular matrix n by n. It has n choose 2 entries. So you want to factor it into n choose 2 of these elementary factors e sub I of t. Of course, first you need to decide on the order of where you place these parameters. And it cannot be just any order because, for example, if there are 2 consecutive matrices with the same location of t, then their product is again a matrix of the same kind, so the dimension drops. It looks like you have 2 parameters, but in fact only the sum of them matters. Okay? And so you ask this question, what are the factorization schemes, the combinatorial patterns that one should use in such factorization? And this is not hard to answer. The answer is that the locations of these parameters should form a reduced word for W naught, for the longest permutation. So in case you don't know what that means, so let's say for 5 by 5 matrix, you need to take a picture like this, where you have 5 lines, pseudolines, that begin on the left and on the right, and each of them intersect any other in exactly one location. So these are pseudolines. So they are like lines, but it's not true that it can be straightened always because the corresponding oriented matroid may not be realizable. Anyway, that's not true. So you take a picture like this, and then you just record where you do the switches. So you view this as a picture in phase space. You have 5 ants on a line. This is space. This is time. And your ants, they move along the line. As time goes by, the vertical cross-section tells you the locations of the ants. And occasionally 2 ants switch their locations, right? And you want them to completely reverse their order. By the end of the day, the ant that was in the rear guard is now in the avant-garde, right? There's now the first one, and so forth. Right? Okay? So if you record the locations where the switches occurred, that gives you a sequence, in this case, 2, right? Because you switch the second and the third guy. It's like doing this between the second and the third. And then maybe this one is a little bit to the left. So this will be 3, and then 1, and then 2 again, and this one is 4, and this one is 3, 2, 1, 2. Okay, so a sequence like this is called a reduced word for the element of maximal length in the symmetric group. You may wonder why such a long terminology for such a simple concept, but this is a special case of something much more general. Okay, so I'm telling you that we have to make a pattern like this, otherwise it just won't work for dimension reasons. The image of the multiplication map along a different pattern will have smaller dimension than n choose 2. And by the way, any such sequence is exactly of length n choose 2 because any 2 lines cross exactly once. Okay, so then the question is, what are the factorization parameters? And you would think that the factorization parameters are some ratios of minors of your matrix, and after all, this is like linear algebra. I mean, what else can happen? And so you take Maple or some other symbolic computation program, and you do this, and you factor, and you look at the formulas, and they are not. For small matrices, they are, but starting with like SL5, there are irreducible factors in the formulas for these factorization parameters, which are not minors of the original matrix. Now we know that there are certain cluster variables, blah, 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 but forget it. So what are they? And the answer is this, that they come from minors, but not of the original matrix, but of a twisted matrix. So what you need to do is you need to take a twist. So if the original matrix was X, this is the original matrix that we're trying to factor. And we want to do something to this matrix before taking the in Russian, matrix is female, so that's why. Freudian slip. It's minors. So what do? We take our matrix. It looks like this. Right? We flip it like that. Multiply on the right by W naught if you want. But okay, we flip it. Then, this is no longer an upper triangular matrix. We take its Gaussian decomposition. Lower triangular, diagonal, upper triangular. Then take well, I guess then one needs also to rotate by 180 degrees, but it doesn't matter. It doesn't change the minors of the matrix. Okay, so basically the transformation is that you start with an upper triangular matrix, and you end up with another upper triangular matrix. But by going through this very simple process. Okay? And then the formula is this. Well, okay, then I'll just say that you need to rotate, but whatever. I'm rushing now and not thinking clearly. So, but the idea is this. Let's say you want to know this parameter t that corresponds to this crossing. The formula is this. You need to multiply. You need to decide for each of the regions surrounding this point, which of the lines pass below that region. Okay. So, for example, here you have 1, 2, 3, 4, 5, and for this particular region, only line number 3 passes below. And here also line number 5 passes below, and here also line number 4. And then you take the flag minors of the twisted matrix, meaning minors which occupy the first several rows and a given subset of columns. Okay? And you take the product of the two minors of the twisted matrix, which are above and below the crossing point, and divide by the product of the matrix on the left and on the right. Okay? But you do this not for the original matrix, but for the twisted, which I defined almost exactly, but you can look it up in the paper. So again, you may wonder, like, does it have to be so complicated? And the answer is, well, yes. I mean, that it is what it is. You don't choose to make it simple, but you can choose to make it, you can work to make it clear. And with that, I will end my lecture.
Thanks very much. Are there any questions? So maybe it's silly of me to ask this when Arkady is in the room, but this stuff with the triangles, I mean, was this before the stuff with loose state parameterizations and the canonical basis?
Yes.
Okay. There's an easier proof than that. Because that's the answer I would have given to the question of how do you prove
Maybe I can comment that the original rule was obtained by Andrei Zelevinsky around 1995. It was not symmetric, but it was polyhedral. And what we did, we just translated it to more symmetric form.